Hi, finally full proof of the strong law of large numbers. Strong law of large numbers, theorem of course. Let xi be IID, finite mean, which mean of course doesn't depend on the I because they have the same distribution. Then the sum of the first n divided by n converges to the mean of each of these, which is the same, almost surely. No second moments needed. Okay, that's the full Kolmogorov strong law of large numbers. Let's prove it. So now we have everything we need to prove this. It's going to be a long proof. I'm going to prove it for the case of mean zero random variables. If e of xi is 0, if this is not the case, then you subtract the mean of the xi's and the proof applies for the center random variable, and that will give you the full statement. So I'm going to assume that the mean is 0. If not, just subtract the mean, everything works through. Okay, so the first step is going to be this probabilistic lemma we just had in the previous video. Namely, the expectation is bounded by the sum of the tail probabilities. Okay, that's the first step. So I know that the expectation is finite. I cannot apply the lemma on e of x directly because e of x is not positive in general, but the mod of x is. So the lemma required non-negative random variables. The mod of x1 is non-negative, so that's what I apply the lemma on. And by assumption it's finite. Okay, so the lemma says that this is bounding from above the sum of the tail probabilities for this mod of x1 larger than or equal to n. That's my first step. So here I'm using this lemma. Okay, now these random variables x's have all the same distribution. So the probability x1 is larger than n is the same as the probability that xn is larger than n, just because they have the same distribution. It doesn't matter if you talk about probabilities of x1 or probabilities of xn. So this is exactly the same, and this is summable. So these probabilities are summable. So now comes Borel-Cantelli. By Borel-Cantelli 1, we know that these events, xn bigger than n, only happen finitely many times, almost surely. Almost surely, only finitely many of the xn's mod exceed or reach n. Only finitely many times, almost surely, will this event here happen. In other words, after some index, xn will be smaller than n, almost surely. This sum index is of course random. Okay, and therefore we're going to cut the random variables xn. So xn tilde, I'm going to define that as xn if xn mod is less than n, and I'm just going to cut it down to 0 otherwise if xn is at least n. Okay, so this is a truncated version. Okay, what the Borel-Cantelli argument says is that xn tilde differs from xn only finitely many times, almost surely. Almost surely the difference, there is a difference between x and so there is a cut actually happening only finitely many times, almost surely. That's the Borel-Cantelli statement. Okay, it follows that the 1 over n sum I equals to sum from 1 through n of the xi, this moving average, this average, goes to 0 exactly when the same average of the x tildes go to 0. This is almost surely the same. This is almost surely the same event, because this sequence of the xi's will only differ at finitely many indices, almost surely, in which case these two averages converge. Oops, what I wanted to say here is that this converges to 0. These averages converge to 0 at the same time whenever there is only finitely many xi's differing between x and x tilde. So that was the first step. Okay, I'm going to call this step 1 if you wish. Step 1. Okay, that was step 1. So step 2, I'm going to demonstrate the same phenomena with the expectations. So step 2, I'm going to show you that it doesn't really matter in some sense if you talk about the expectation of x or x tilde. So let me start looking at the expectation of this truncated random variable x tilde. What is the truncated random variable? This is the original random variable xn multiplied with the indicator that xn mod is less than n. So the notation for the indicator multiplying a random variable with an indicator under the expectation was the semicolon notation. So this exactly means what we had in the definition of the x tilde, namely I take xn, but only when xn is less than n. Okay. Now, these xn's are all have the same distribution for every n, and therefore this expectation is equal to the expectation of x1 on the event that x1 mod is less than n. That's just because the distribution of x1 and xn is the same. And these random variables, on the other hand, these are all dominated. So what do we have under the expectation? We have x1 times the indicator. The mod of this whole product here is less than or equal to x1 mod, of course, because the indicator is 0, 1. And x1 mod is a random variable that has a finite mean by assumption, and it does not depend on n. Therefore, dominated convergence applies. And if you look at x1 times the indicator, that x1 mod is less than n, that will of course converge almost surely as n goes to infinity. It will converge to x1. Why is that? Because no matter what the value of x1 is, eventually n will exceed the mod of x1, in which case the indicator becomes 1, and then the product is just equal to x1 itself. So we have a bounding random variable that doesn't depend on n. We have almost sure convergence. This is everything I say is almost sure here. This is almost sure, and therefore we can apply dominated convergence, and this thing will converge as n goes to infinity using dominated convergence to the expectation of x1, which is the expectation of this limiting random variable, which by assumption is 0. So by assumption, the expectation of the xn tilde is going to 0. Notice something important: the expectation of xn tilde itself is not required to be 0. We truncated a mean 0 random variable, but the truncation might alter the expectation. So in general, it is not true that the expectation of xn tilde is 0. However, this argument shows that in the limit, it still converges to 0, the same mean as x1 had, which was 0. And therefore, hence, if you look at 1 over n, the sum of e of xk tilde, the e of xk tilde is a sequence that goes to 0. This is the Cesaro limit. So therefore this thing, this is up to n. This is up to n. This is a Cesaro limit, and therefore if the expectation of xk tilde goes to 0, then the zero limit also goes to 0 almost surely, as n goes to infinity. Okay? And therefore, if we want to find, so what is this proof about? The proof about is to prove that we have almost sure convergence of 1 over n sum of the xi's to 0. We showed in step 1 that this is equivalent to the almost sure convergence of the sum of the xi tilde over n is going to 0. And therefore, we can further show that this is equivalent, almost surely at least on a probability 1 set, this is equivalent to the convergence of 1 over n sum I goes from 1 to n xi tilde centered minus exi tilde going to 0. Okay, so that was step 2. You can actually bring in the expectation of the x tildes under this average. The reason is that 1 over n sum of the x tildes is going to 0 anyway, and therefore if you want to prove, which we want, that 1 over n sum of the xi tilde goes to 0 almost surely, it's equivalent to proving that 1 over n sum of the xi tilde minus exi tilde goes to 0 almost surely. In other words, you can look at the centered truncated random variable instead of just the truncated random variable under this averaging limit. Okay, so this was the first few steps. Let's then proceed with step 3. So adjusting this setup a little bit. Okay, so step 3. Step 3, so what do we want to do? We want to now prove the convergence of 1 over n sum of the xi tilde minus exi tilde to 0. If we prove that, then we can go back to step 1 and then we have the statement. So step 3, we want to prove that, and now I bring you up Kronecker's lemma. Okay, here was Kronecker's lemma. We want to apply this on 1 over n sum of the xi tilde minus exi tilde. So let me rewrite this slightly. 1 over n sum I goes from 1 through n xi tilde minus exi tilde. I would like to rewrite this a little bit by adding an I in front and dividing by I at the same time. Okay, and now I would like to look at this factor bj or bn in front. I want to identify that with the b of the of Kronecker's lemma, and I want to look at the xj's as the x tilde minus exi tilde over I. So this is going to be the xi, this is going to be bi, and this is going to be bn. And then you can see that it's exactly in the form of Kronecker's lemma with these substitutions. So the bi is here, the xi is there, the bn is there, with b equals to n. And Kronecker's lemma tells me that to show that this goes to 0 almost surely, to show that this goes to 0 as n goes to infinity almost surely, it's enough to show that the sum of the xn converges, namely the sum of these xi tilde minus or xn tilde minus exn tilde over n converges. So it's enough to show that the sum of xn tilde minus exn tilde over n converges almost surely. Okay, so that's step 3. Enough to show by Kronecker's lemma that this converges almost surely. Okay, so far so good. So now step 4. Step 4. is to invoke Kolmogorov-Khinchin. Okay, let's invoke Kolmogorov-Khinchin. Obviously, the x tildes are independent. They come from independent random variables truncated by n's, which are not random, so they are still independent. Kolmogorov-Khinchin, if we have independent random variables and mean 0, these guys are mean 0 because we centered them, then if we can show that the sum of the second moments is finite, then we exactly have the convergence of the sum. So Kolmogorov-Khinchin tells me that it's enough to see that the sum of the variance of the x tilde n's divided by n square converges. Okay, so again, the Kolmogorov-Khinchin, if the sum of the second moments converges. Now, what is the second moment of this thing? The second moment brings out a square out of this n, and the second moment of anything centered is its variance. So that's how I get the condition that I need to see that the sum of the variances over n squares will converge. Okay, so that was step 4. And finally, step 5 is to actually show this. So we're going to show this. We're going to go through step 3, step 2, step 1 backwards, and that will prove the theorem. So step 5, let's actually show this. Let's show this. Okay, so how do we show this? So that's going to be a little bit of a calculation. I'm going to start off with exactly this quantity, this sum from 1 through infinity of the variance of xn tilde over n square. The variance is always bounded from above by the second moment. So I can actually look at the second moment of xn square tilde over n square. Okay, so what was that? Well, the definition of the xn tilde was that it was the original random variable xn truncated at n. So I'm going to put that back in now. So this equals to the sum from 1 through infinity, 1 over n square, expectation of the original xn square random variable, but only if xn is less than n. Okay, by the way, why did we do all this truncation? Of course, because we are able to talk about the variance of the xn tilde. The xn tilde never exceeds n, so that's why it has a finite variance, and that's why we could apply all these theorems we had before. Okay, so what do I do with this one? I'm going to break up this event into intervals of length 1 in the following way. This indicator tells me that xn mod is less than n, which means xn mod needs to be in some integer interval, and that's what I'm going to kind of formulate with the following breaking up of the indicator. So I'm going to, instead of looking at this event that xn is less than n, I'm going to say it's at least k minus 1 and at most k, actually strictly smaller than k. So these are indicators which are mutually exclusive. For different k's, it cannot happen at the same time that we have this indicator. However, the union of these events exactly spans the event that xn mod is less than n, sorry. And therefore, if I do a summation on these indicators, that sum will give me back the indicator that xn is less than n. So it's just a breaking up of this event into intervals where xn could be. Okay, k goes from 1 means I start from 0, which is fine, and k goes up to n means I'm ending up n, which is again fine. Now, under the expectation, I can actually change the nth index for the random variable into the first index, x1. That's again because the x's are iid. So I can replace xn by x1 everywhere. And that's because the x's have the same distribution over all indices. Okay, so all I did was replacing n by 1. And what I want to do next is, of course, the mathematician reflex. I see a double summation, immediately I want to swap them. So I want to write the summation in k first. And what is the double summation? It tells me that n is at least 1 and k is at most n. So in fact I have this range for my summation. K is between 1 and n. And so if I start with k first, then k will go from 1 to infinity. If I fix k, then I see that n will start from n to infinity. So I'm going to go from 1 to infinity. I'm going to go from in n from k to infinity. I'm going to have the 1 over n square, and I'm going to have the expectation of x1 square on this interval k minus 1 less than or equal to x1 and strictly less than k. Strictly less than k. Alright, notice that on this right hand side nothing depends on n anymore, so I can as well look at this sum separately. And everybody is non-negative. This is a square, this is an indicator, everybody is non-negative. And now comes lemma 1, this calculus lemma we had before, namely if k is at least 1, then 1 over n squared summed up from 1 to infinity, lemma 2 or lemma whatever it was, lemma 1 over n squared summed up from k to infinity is bounded by 2 over k. So I'm going to replace this sum by the upper bound of 2 over k. Okay, and then write sum, k goes from 1 through infinity, 2 over k, and the same expectation, x1 square under the condition or under the event. It's not a condition, it's multiplying with an indicator, so it's not a conditional probability. Under the event that x1 is between k minus 1 and k. Okay, and now comes essentially the last step, namely under this indicator, the mod of x1 is strictly smaller than k. So under this indicator, x1 is smaller than k. So x1 square under the indicator, x1 square times the indicator that k minus 1 less than x1 mod less than k. For any real number, it doesn't matter if I square it with a mod or without a mod. So I'm going to add in the mod, and then under the indicator I know that the mod is less than k, and therefore the square of the mod is less than one of the mods only, times k under the same indicator. K minus 1 less than or equal x1 less than k. That's simply because when the indicator holds, then x1 mod is less than k, so the square of x1 mod is less than x1 mod times k. When the indicator doesn't hold, then both sides are 0. So maybe I should add here an equal. Okay, and therefore this is smaller than or equal to the sum from 1 through infinity. And now what I'm going to do, of course, is plug this in the expectation. K is not random, it comes out of the expectation and kills the 1 over k in front of it. And that leaves me with a 2 and an expectation of x1 mod only without a square, and the indicator k minus 1 less than or equal to x1 mod less than k. Okay, now if I sum this up from 1 through infinity, that means that I look at all possible values of x1 mod. When k is 1, I start from 0, and I look at all possibilities for x1 mod. These indicators are mutually exclusive. Almost surely x1 mod is a finite number, and therefore when I cover every interval like this, like k minus 1k, then I will cover every value of x1 exactly once, and therefore these indicators just sum up to 1, and I simply end up with twice the expectation of mod x1, which I assume to be finite. And that's the end of the proof. I just proved that the sum of the variances of x and tilde over n square is finite. That's what I needed exactly in step 4, and then that's whatever I concluded in step 4, but was what I needed in step 3, and then back to step 2 and step 1, and finally I proved my theorem.